If you are wondering if your regression model is performing well or not, you are at the right place. Hello and welcome to Machine Bytes. In today's video, we will learn about how we can verify the accuracy of our regression model. In last videos, we learned about how we can create a regression or classification model from scratch. So when we do the regression, we generally do have full data, which is further divided into training data and testing data. On this training data, we train our ML model, which is used to make the future predictions. Now, this testing data has both the columns for features and the target variable. To test how well our model is performing, we pass the features of this test data to our ML model and we get the predicted values. Now we have two sets of target values for this target set. One is the actual values, these are the actual values, and these are the predicted values. Now to measure the accuracy of this particular model, we need to compare these values. And from that, we can tell how well our model is performing. In today's video, we will learn about these approaches, which are MAE, mean absolute error. Then we have mean squared error. We have root mean squared error. Then when we have is R square value and adjusted R square. Let's explore these one by one. Mean absolute error. If we consider we have some actual target values and then the predicted values. If 10 is the actual value, 12 is the predicted, or 11 is the actual, 10 is the predicted. In this case, the difference between these two is if we do actual minus predicted, -2 and 1. So we got the difference in two different directions. Mean absolute error will take the modulus of this value and that will be treated as MAE. So it will be 2 and 1. If we want to visualize this, it is something like this. So let me try to draw it again. If these are the data points and this is the regression line, now we can see that for this particular point, this is the actual Y value, but this is the predicted Y value. So this is the difference between actual and predicted value. In the same manner, for this point, this is the actual value while here is the predicted. So this is the difference between actual and predicted. If we have a point here also, then this will be the difference between actual and predicted. So in case of mean absolute error, we are just taking these differences without considering the direction in which points are deviated from the regression line. So formula for MAE will be yi minus yi hat its modulus. This will be for one data point, but we want this for all the data points. So we will do a summation from 1 to n and divide everything by n to take an average. So if we talk about this case, in this case, the summation will be 3 and we will divide it by 2. So the final value will be 1.5. We can say in this case, on average, the predicted values are deviated by 1.5 units from the actual values. Let's talk about some advantages of MAE. The one of the advantage is same unit. Like I talked here, so if these values are 10, 12, 11, 10, we can say the predicted values are on average 1.5 units deviated from the actual values. So the unit here is same as of these values. So it's easier to compare the deviation that is there. Then the other advantage is it's robust to outliers. What does that mean is if there is an outlier, for example this, it will not make much difference to the overall value of MAE. There will be some difference, but still MAE will be able to absorb that. Let's talk about disadvantages of this. The major disadvantage of MAE is that its loss function is not differentiable. So the loss function for MAE looks something like this. So we can see here at 0, it's not possible to differentiate function. At other places also, differentiation is done in steps. So the optimization is a complex process. The other disadvantage is because this log loss function is not differentiable, the convergence takes more time. That's about MAE. We have other metrics also to evaluate our regression model. The next one is MSE, which is mean squared error. The mean squared error is able to resolve the issue with MA with respect to convergence. So in case of MSE, the loss function looks something like this, because of which it is possible to differentiate it. Formula for MSE looks something like this: yi minus yi hat whole square. This will be for one data point, but we need to sum up it for all n points. So to take the average, we can divide it by n. Now, this is one of the advantage of MSE, that its loss function is differentiable. The other one is it has only one local or global minima. These are some of the advantages of MSE. But if we talk about disadvantage, then those are also there. One of them is now because we are squaring the value, it will lead to penalizing the outliers heavily. So we can say it's not robust to outliers. The other function that we will study today is RMSE, which is root mean square error. As this suggests, RMSE is nothing but root of MSE. Okay, I missed one. There is one more disadvantage here, that is the unit of MSE is not same as given values, because we have that already squared that. Let's come back to RMSE. RMSE is nothing but square root of MSE. So now this thing is corrected here. Unit again is same. And the other advantage of MSE is also present here, that is, the function is differentiable and hence can be used as loss function. If we talk about the formula of RMSE, it will be yi minus yi hat whole square divided by n, which is summed from I to n and square root of whole thing. The next thing is R square value or coefficient of determination. These all are names of R2 score. Now, as the name suggests, it is not the metric to evaluate the performance of our model, but it helps us to find goodness of it. What does that mean is if we are given maybe feature 1, feature 2, and target value, and consider we have fitted linear regression over this. Now, our 2 score will tell us how well these two features are able to explain the target variable. So, if we say that our R2 score value is 0.8, then we can say that feature 1 and feature 2 are able to explain 80% of target values. So until now, the other three metrics which we read were dependent on the context. For example, MAE, MSE, or root mean square error. If the result is coming to 4.5, that is 4.5 deviation from the actual values. Now, 4.5 can be a huge number in some cases for sensitive areas, whereas for some other broader categories, 4.5 might be a very small number and can be ignored. So this is use case specific. But when we talk about R2 score, it is independent of use case. If we are saying R2 is 0.8, in all the cases, it means the same thing, that our features are able to explain 80% of target variable. Formula for R square is 1 minus sum of squared values of regression line divided by sum of squared values of mean line. For example, if here we are trying to predict salary on the basis of experience. So the data points will be something like this. As the experience grows, the salary will also increase. Now, if we do not take experience into account, our mean salary, we can draw a line something like this. So this is our mean line. But when we took the salary into consideration, our regression line may look something like this. So this is our regression line. Now, for example, this data point, this is the difference from regression line, while this is the difference from mean line. So we need to take sum of square of all these differences for regression and mean line. And that's how we have the formula for R square. Let's see when R square can be 0. So to have a 0, we need to have second term as 1. Then it will be 1 minus 1 is equal to 0. And second term can be 1 only when these both two values are equal, which means that our regression line and mean line are same. The other case could be when R square is equal to 1. Now, to have R square as 1, we need to have second term as 0 and Second term can be 0 only when numerator is 0, which is sum of square of regression line is 0, which means our regression line is not making any mistake. Is perfect or near to perfect. The other case where r square is less than 1 is, less than 0 is when the ratio for second term is greater than 1. Which means when our regression line is making more mistakes than our main line. This can happen when we have chosen the wrong model for our data, where even the mean line is making more sense than the regression line that we have picked. Topic for today is adjusted R square. Adjusted R square is nothing but a variation of R square, which is 1 minus 1 minus R square, which is the normal R square, n minus 1 divided by n minus 1 minus k. Here, n is number of rows and k is number of features. Let's understand why was there a need of adjusted R square when we already had R square. So in case of R square, what was happening that even when some irrelevant features were added, then either R square was increasing or remaining the same. But instead of that, what should have happened that R square should have dipped. Let's take an example. If we have a feature, for example, experience, rating from past year, and salary. So R square at this moment is dependent on how experience and rating are able to explain the salary of a particular employee. Let's say this is 0.8 at this moment. But now if there is one more feature added here, which is home location. Now, in real world, there should not be any impact of home location on the salary of a particular employee. So adding one more feature should decrease the R square value. But that is not the case with R square. Instead, either R square will increase if it is able to find out any relevance which actually is not correct with respect to home location, or it will remain the same. So it will give us the incorrect picture of how features are able to explain the target variable. To eliminate this problem, adjusted R square came into the picture. Now, if you see here, the overall term is being divided by a number of features. Let's understand this with help of an example. So when an irrelevant feature is added to our dataset, in that case, our k will increase, number of features will increase. So this overall term will decrease. And in R2, either there will be a slight change because the feature is irrelevant. So it will either increase very slightly or there will be no change. And this term is constant. So we can say this whole term is approximately constant in this case, but denominator is decreasing. So since denominator is decreasing, this entire term will shoot up. And since 1 minus something will shoot up, it will result into a lower R2 score. Now, if we take another example where some relevant feature is added. Now in that case again, the K will increase. So this overall term will decrease. But now there will be a shoot in this term R2 because this is a relevant feature. If there is shoot in this term R2, so 1 minus R2 will decrease very heavily. So this decrease is so much big than this decrease. Now we can say that this second term, entire term, will decrease overall. So if we will subtract something decreased from R1, our R2 score will increase. We talked about different metrics, which are mean absolute error, mean squared error, root mean square error, which will tell us how deviated are predicted values from the actual values. Then we have R square and adjusted R square, which tell us that how well our features are able to explain the target variables. So in this case also, the output that we are getting is in different units. So it's not easy to tell customers how accurate our model is actually. So to do that, what we can do is we will have our actual values. We will have predicted values. For example, if it is 10, here it is 15. Then if we have 10 here, 12 here, or 20 here, and 15 here, something like that. And if we are picking mean absolute error as our metric, then it will be 5, 2, and 5. So to generalize it, what we can do is we will find absolute percentage error. Now, if we see here, the average MAE will be 12 divided by 3, which is 4. So on average, our actual values are deviated by 4 while predicting the final values. Absolute percentage error will be MAE divided by actual value into 100, which will be 50% in this case. Here it will be 2 divided by 10 into 100, which is 20%. Here it will be 5 divided by 20 into 100, which will be 25%. So if we take mean of this absolute percentage error, then it will be 50 plus 20 plus 25 divided by 3, which is 95 divided by 3, 31.6. So to generalize, if you want to tell how accurate your model is, accuracy will be 100 minus mean of absolute percentage error. So in this case, it is 100 minus 31.6, which is around 70%. So in this case, the accuracy of our model is 70%. Now this is a standard term. Even if we are calculating here either root mean square error or mean square error, this final term will be in same units, which is percentage of how accurate our algorithm is performing. We have learned majorly MAE, MSE, and RMSE, then R square in this video. There are some advantages and disadvantages associated with all these approaches. So in our real-time scenarios, we need to choose wisely which metrics we should focus on and should be treated as our final metric. That's all for this video. Let's continue our learning in upcoming sessions. Thank you so much.